This video is all about integrating trigonometric functions. Now we know that when we differentiate sine x, we get cos x. We proved that by differentiation from first principles. If you need a recap of that, watch the first video from the Year 13 differentiation playlist. So that makes sense then that if we go the opposite way, so if I were to integrate cos, I would get sine. Similarly, we proved by first principles that when we differentiate cos, we get minus sine. So again, it makes sense that if we were to go in reverse, if I was to integrate minus sine, I would get cos. Or if I was to integrate sine, I would get minus cos. So this little cycle here is a nice way of remembering the pattern. So we know that sine differentiates to get cos. We know cos differentiates to get minus sine. We know minus sine differentiates to give minus cos. And we know minus cos would differentiate back round to sine. Integrating just goes the opposite way. So if I was integrating cos, I would get sine. If I was integrating sine, I would get minus cos. If I'm integrating cos, I get minus sine. If I'm integrating minus sine, I get back round to cos. Really, all you need to remember is sine to cos to minus sine. Really, that's the bit there that you need to remember for differentiation, and then that way for integration. There are other results we know as well. These are the results that are on your formula booklet. Now, you've probably heard me ranting about this already, that I don't like the way that these formulae are presented to you. I don't like the fact that there's K's everywhere. I won't bore you with the same rant again now. I don't think those K's should be there, and when you look at these formula sheets, completely ignore them. Completely ignore those K's, pretend like they're not there. Here's my version. I've already just removed all of the K's from this formula sheet, and it's much nicer to use now. So, we have already proved from the quotient rule that tan differentiates to give sec squared. We've proved that sec differentiates to be sec x tan x, and so on. So those are differentiation rules, but we can use those in reverse. We know that sec squared would integrate to be tan, which you are also given over here in the integration section. But there are other formulas here that are not given in the integration section that can be useful. So for example, the sec x tan x, that would integrate to be sec x. The minus cosec squared would integrate to be cot. Or if if that minus wasn't there, if I was just integrating cosec squared, that would integrate to be minus cot. If I've got minus cosec x cot x, that would integrate to be cosec x. So we've got some hidden integration rules within the differentiation section of the formula sheet. And then we've got all of the integration formulae as well. We know that sec squared integrates to be tan, as same here. We have previously shown by integration by substitution that tan is going to integrate to be ln sec. And we showed that cot is going to integrate to be ln sine. Integrating cosec, there's two different versions of the result here that we can prove using identities. Either this or this, and the same with sec. If I'm integrating sec, there's two different ways that I can write out the answer. So we've got lots of different formulae here to help us to integrate trigonometric functions. And we've proved all of these either by differentiation or by integration by substitution. The rest of this video is about how we're going to use those formulae in some simple examples and some harder examples. So here's a relatively simple one. It's simple because all of these functions integrate pretty straightforwardly without needing any identities. The cos is going to integrate to be sine. So when I integrate cos, I get sine. Nice and simple. Next, this cosec squared. Well, I know that minus cosec squared would integrate to be cot. So therefore, cosec squared is going to integrate to be minus cot. And I've got 3 of them. Next, we've got the 4 tan 2x. Now, don't worry about the 2x here. We can deal with that with the reverse chain rule. I'm just going to integrate the tan function, and then we'll divide by 2 afterwards because of the 2x. So integrating tan, let's look on the formula sheet. Where's that? Integrating tan. If I want to integrate that, I'll get ln sec. So I'm going to have 4 lots of ln sec 2x, and then I need to divide by 2 because of the reverse chain rule. The 4 divided by 2 is 2. And don't forget your plus c constant of integration on the end. Next, we need to integrate sine over cos squared. Now notice that none of that is on the formula sheets. There's no formulae either here or down here for sine over cos squared. So I need to rewrite this first. I know I can think of this cos squared here as cos times cos. So I'm going to unsimplify this first. Here's my cos squared. And that's helpful because here's tan. Here is sec x. So we've got the integral of tan x sec x. So I can now look at the formula sheet. Do I have the integral of tan x sec x? Or do I have the integral of sec x tan x? They're the same thing. We can change those around. It doesn't matter. And the integral of sec x tan x, I can see that's here. This line here is telling me that sec differentiates to be sec x tan x. So therefore, sec x tan x is going to integrate to be sec x. So the sec x tan x integrates to be sec x, and don't forget your constant of integration. Next example. I want the integral of sec x plus tan x all squared. So I'm going to expand the brackets first of all here, because I can't do any integration whilst we've got that squared there. So we're going to have sec x squared next we're going to have sec x times tan x, but there will be 2 of those when I expand out those brackets. And then we're going to have tan x squared. Right, now I've expanded those brackets, I'm looking at each of these terms and deciding whether I can integrate them or not. The sec squared, I know that's going to integrate to be tan. So that's pretty straightforward. The sec x tan x, I know that's going to integrate to be sec x. So that's pretty straightforward. The difficulty is in the tan squared, because that's nowhere here and it's nowhere here. So I don't know what tan squared integrates to give. So now I'm thinking, how could I rewrite tan squared in a different way so that I can use one of these formulae over here? Well, I know that tan squared is the same thing as sec squared x minus 1. We should hopefully know that squared identity by now. If you can't remember where that came from, just remember that sine squared plus cos squared is identical to 1. And if we divide through by cos squared, we get that tan squared plus 1 is identical to sec squared. And therefore, tan squared is identical to sec squared minus 1. So, by rewriting that tan squared as sec squared minus 1, I can now group up these sec squared terms together. So I'll get 2 sec squared x plus 2 sec x tan x minus the 1. And now all of these things are going to integrate easily. The sec squared is going to integrate to be the tan. The sec x tan x is going to integrate to be the sec x. And the 1 is going to integrate easily as well. So I'll get 2 tan x plus 2 sec x minus x plus the c. And there we go. So the idea of this is that if we have something that's on the formula sheet, great, integrate it, no problem there. If we have something that's not on the formula sheet, then we need to use a trigonometric identity to turn it into something that is on the formula sheet. So really important you know your identities. One identity is especially important for you to know. It's the cos double angle identity. You're not given the cos double angle identity, but it's pretty easy for you to work out, and part A of a question might get you to prove it. We can prove it by starting with the cos addition formulae that's on the formula sheet, and then just swap the B to be A. That way we'll have a cos 2A, and then we have a cos squared A and a sine squared A. And that gives us the basic version of the cos double angle formula. Remember that there are 2 different versions of that. In this example, I want the version that has sine squared only in it. So, I'm going to rewrite that cos squared as 1 minus sine squared. Which then allows me to collect up those sine squared terms, like so. Now I'm going to make sine squared the subject. So I'm going to add 2 sine squared to both sides, and I'm going to subtract cos 2a from both sides. And then I'm going to divide both sides by 2. This will now allow me to turn this sine squared into a 1/2 minus 1/2 cos 2a, which is a lot longer, but it's also a lot easier to integrate. Because the 1/2 is going to integrate to be 1/2 x, and we know the cos is going to integrate to be sine, so we'll have 1/2 sine 2x, but we need to remember to divide by 2 because of the reverse chain rule. And so when we divide by 2, this will actually become 1/4. And don't forget your constant of integration. So when we are integrating sine squared, we need to use the version of the cos double angle formula that only has a sine squared involved in it. Really important we remember to use that. If we're integrating sine squared or cos squared, I'm going to show you a cos squared example in a minute. If we're integrating either sine squared or cos squared, then we need the cos double angle to do that. So let's have a look at a cos squared version. I've already shown all my working out for this. Now in this case, a slightly more complicated one. We've got the cos squared here. I've also got a 5 here and a 6 at the front. Don't worry about the 5 or the 6 though. We can adjust for those later. The 5 we can adjust for with the reverse chain rule later by dividing by 5 at the end. The 6 will just make my integral 6 times bigger, so don't worry about that. The key thing here is the cos squared. So because we are integrating cos squared, we're going to start with our cos double angle, just like we did in the previous example. Except this time we want the version that only has cos squared involved in it, so I'm turning the sine squared into a 1 minus cos squared, which then takes me to this identity here. Just like in the previous example, we're going to make cos squared the subject. That's what I've done here. Now, let's look at the fact that we had actually a 5x on the inside here. So if here I've turned that a into a 5x, which means the 2a would be a 10x. So we can see here that I've taken the cos squared 5x and turned it into a 1/2 cos 10x plus 1/2. And then it needed to be 6 times bigger. You can then see that I've multiplied through by 6 to get 3 cos 10x plus 3. And then I can integrate. The cos integrates to be sine. You can see I've remembered to divide by 10 because of the reverse chain rule. And the 3 integrates to be 3x. And we've got the plus c on the end. So the point of the last two examples is that we can always use the cos double angle to integrate either sine squared x or cos squared x, and we can adapt if we have numbers on the inside. Now, we are only going to do that if we have a nice simple sine squared or cos squared written as they are. We're not necessarily always going to do it, as you can see in this example here. This question says to integrate 1 over sine squared. Now, whilst I'm allowed to change that sine squared into 1/2 minus 1/2 cos 2x, that's not wrong. It would just be a ludicrous thing to do. Because I've made this integral a lot harder by doing it. I could actually have just turned that 1 over sine squared into a cosec squared. And then we know how cosec squared integrates. It's with minus cot. So I just wanted to make the point here that whenever we're integrating sine squared, nice simple sine squared like that, or a nice simple, 3 cos squared, integrating nice simple ones like that, you must use the cos double angle to do it. Real common question there. Real common technique, you need to know how to do it. However, there are other ways if we have other things going on as well. So key things from this video. Remember, you've got the differentiation part of the formula sheet, which also tells you about integration. If something is not on the formula sheet, then you are going to use your trigonometric identities to turn it into something that is on the formula sheet. And if we have a sine squared or a cos squared, remember that cos double angle.